name of this theorem, so I'm going to state it. F is analytic on R, so I don't multiply connected region, then all nth derivative exists, and they are analytic. And analytic in the same region. So I think I should show this one first. Let me show you this important function. If you go to grad school, and not necessarily majoring mathematics, if you're in statistics or some sort of applied math, all of them will require to study a little bit of analysis. No matter where you are, how applied it is, they'll require a little bit of analysis. And this is most fun item they throw at you at the graduate level. Here's a function. This is called Weierstrass function. It's a mathematician that shocked the entire mathematicians. Back then, many people relied on intuition. Continuity in differential geometry, and physicists, they rely on lots of intuitive notion, and this just shocked everybody. And he had a couple of examples. So this function is called a differentiable nowhere. It's kind of tiny, but it says they're differentiable nowhere. Okay, but it's continuous. That's the strange nature of this function. The way it's constructed originally is this type of that. It's a sum of this infinite cosine, so it's like a Fourier series. But the way coefficient is involved, an and bn, for each of the term, it satisfies a certain condition, and they generate this weird fractal shape. If you go zoom in, it never stops. But miraculously, it's continuous, and there's nowhere it's differentiable. So it looks like this. It's from Wikipedia. If you Google nowhere differentiable, the first item will show up is this one. And with my following idea, I actually published this one. It's like simple idea, and they decided to publish it. Let me share it with you. Here's an important example. This f of x is a nowhere differentiable function. Nowhere differentiable function, but continuous. From the real example, there is a function, it's all continuous, but not differentiable at 1 spot, 2 spot, 100 spots, right? Those are taught in the very beginning of the Calculus 1 level. But the nowhere differentiable is kind of unthinkable. But he constructed it. So everybody knows that, but it seems like nobody really think about the following. Whenever the function is continuous, its antiderivative exists, right? Do you know what theorem is that? We just seemed like did something like that in a complex version, but the real version is more important. This is Riemann's integrability theorem. It is right in that Calc 1 book, but we never go into the proof of it. But however crazy and fractal nature and pathological it is, as long as the function is continuous, its antiderivative exists. You just can't find the formula. And that Weierstrass one that I showed you, because it's nice behave in absolute convergence, you can simply integrate this one. And I began to sketch the antiderivative in this one, and I found an interesting thing. But here's the thing. This is a very good example. I'm going to call this one an antiderivative of f of x. How do you know antiderivative f of x exists? It's Riemann's theorem. Whenever function is continuous, there is an antiderivative, right? So that, what is the idea? F prime of x as a real differential function is little f of x, right? So isn't this differentiable function everywhere? Because its derivative exists and it is f of x, right? So we're staring at this function right here, which is differentiable. And when you differentiate it, and it became this f of x. What is this f of x? It's continuous, but you cannot differentiate any further. Isn't that right? That's the situation in real. Go back to complex. If it is differentiable everywhere, then the first derivative is still differentiable, and second derivative is still differentiable, and third derivative is still differentiable, which is not the case in the real numbers. And this phenomenon is considered the most mysterious phenomenon in a complex number, just because the condition is all around. But if you compare it here, this condition just induces all the other nice behavior, kind of indicates that this is actually the right domain to look at to pose good condition on a function. If you look at the real, which is more natural, but it doesn't tell you the whole story. Therefore, this phenomenon tells you that that's the right domain to look at the complex numbers. Once analytic forever and exist. All right, so one thing that going toward the proof of this is really nice, and it's application of the things that you have learned so far. So first one is this Cauchy's formula. This version, f prime of a equals, this is 1 factorial, 1 over 2 pi I, and circle that contains this singularity in there, f of z. This is not correct, is it? This formula? How do you fix this formula? Z minus s squared. Thank you. That's the formula. So that was advanced problem today's homework. Was that okay? Did you make sense out of this? You still have the same linear approximation in there. I ask you to use that linear approximation to conclude this one really picks up the f prime of a. Was that all right? I'm going to post that solution. But now we have it here, and other versions are second prime and right there. But you didn't really think about, when you enter, the student usually don't think about, when you enter this formula, didn't think about, all right, the formula means the second differentiable and third differentiable, and those values are equal. Let me say that again. If you look at other versions of the Cauchy formula, it said left-hand side is a double prime, and this one power increases, right? But that statement really says threefold. Left-hand side exists, and right-hand side exists, and they're equal to each other. So that formula actually contains a statement that all the higher derivative exist, right? So, but we got this one for free because f prime of a exists, right? Because the condition is analytic. So f prime of a, and we got this formula. From here, everything is going to fall out. So I'm going to show you, using this formula, we supposedly proved it, using just linear, but going to the next level is a subtle. And here's a corollary, is that f prime of z is continuous on R. So if you have analytic function, and if you differentiate, because of the analytic property, it's easy to say f of prime of z exists, right? That's all this analytic says. Everywhere, f prime of z exists. It doesn't imply it's a continuous. It doesn't imply it's analytic, right? All that it says, and f is analytic, is that this one exists. Everywhere we have a derivative. Okay? But it doesn't say it's continuous. But we're going to say it's a continuous. Once we establish the continuity, analytic falls apart, and it comes really easily with other theorems. So this turns out to be the most hard part. So we're going to use this theorem to prove that. As a proof, it goes like this. Let B approaches A, and A is fixed. We want to show f prime of B, f prime of A. They all exist, right? What is the symbol that goes between this? if we want to show the function is continuous. Now fa is fixed, b is varying, right? Therefore f prime b is varying. What do we want to say as b approaches a, right? What is the symbol? Not equal, but arrow, right? This approaches that. That's what we want to show. If we establish that, it's continuous at a. Therefore, it's continuous everywhere since a is a random number. So we try, just ease the notation. We're going to try this one. 2 pi I is a constant, right? But you know where the 2 pi I come from. Anybody know where the 2 pi I come from? Cauchy's formula, right? So we're applying the Cauchy's formula. So what do you see there? Integral, right? Integral of c, whatever the c is, must contain b and a, right? Must contain b and a. So what is it? F of z, on the right, divided by z minus b squared dz, right? That's what this f prime of b part is, right? Minus c, how about this one? fz divided by z minus a squared and dz. Okay, let's say c is here, oriented this way. A is there, and where is going to be b? B is going to be really close to a. Isn't that right? That's the situation. We're not interested in b over there. We're interested in b very close to each other, right? So that's the situation. C doesn't change, some fixed 1, maybe with radius 1. Okay, let's say this radius 1. And B is really, really close to A. So we're going to do this. We're going to put this integral together, fz, and do some algebra. So z minus b squared, z minus a squared, right? So I factored out fz there. So who can do the first term? Cross multiply, so you see the z minus a squared minus z minus b squared. Agree? Good. So let's simplify the numerator. So fz there, and what's the numerator? Z squared cancels, right? There's negative 2bz, but it's going to be positive 2bz. So let me write 2bz there. Here you have a negative 2az as your square, right? So here's negative 2az in there. We get negative b squared here. So negative b squared. And we have a positive a squared, right? But inside the parentheses, you have to go like this. Now, if some of your students are looking at b squared minus a squared, and what comes to your mind? Is something automatic you do, b squared minus a squared. B minus a, but b plus a, right? And what is that here? 2 times b minus a, right? So we're going to factor out that b minus a has no... It's fixed, right? What is integral is going around the circle, and b is relatively fixed for that integral. So b minus a factored out, and what do we have? F of z, 2z, what's left here? B plus a, right? And z minus b squared, and z minus a squared, dz. Does that make sense? So here's the thing. The difference between these two values is difference between input value times something. If we can show this one doesn't go to infinity, here's a small quantity, right? Then this whole quantity is controlled by b minus a. Therefore, it approaches 0. Okay? So this is a prevailing idea of entire analysis that involves actually real and complex both. To getting this one is very important to understand those analysis things called, and which is required in every field and in the training period. All right. Now, next thing is that we're going to look at absolute value and show that this absolute value is an interesting part. So let's enter absolute value of 2 pi I fb minus fa is going to be less than or equal to an absolute value of b minus a, right? In the circle. Now remember, when you enter absolute value, you have to change that integral to real value integral. It's going from 0 to 2 pi. Remember, it's going around the circle with radius 1. So f of z, where the z is a plus, the center at that is it. That's the situation. Radius is 1, and b is very close to that. So z is actually parameterized with this one, and now you put absolute value everywhere, right? How about this one? You can use a triangle inequality. You can put 2 absolute value of z, that changes to plus b minus b plus a. Absolute value everywhere, and you kind of increase, turn everything into sum, and that's actually the bigger. And this one was radius 1, so there's radius 1 in there. Right? Z minus a has radius 1, correct? And there's this dz dt that looks like I times eit, but that's always 1 in this scenario. It's ddt. Only thing you have to take care of is what is happening with the z minus b. So here's a picture. A is here, and b is very, very close, right? And there's our z's, and there's where b is. Correct? So this is z minus, absolute value of z minus b squared is the distance between the z and b. And that's what this one is measuring, right? So if I line up a to b like that and call that one z0, don't you think that's the smallest distance, shortest distance there? That if the z is over here, then that's the distance there, right? That's what this one is measuring, z minus b. And if you go crazy, it's getting longer and longer. There's right across that, when they're collinear, that gives you the shortest distance, correct? And what is that shortest distance? Definitely greater than 1/2. Where does the 1/2 come from? Just arbitrary number. B is very, very close to A, right? So I can say this one is greater than or equal to, if I replace this one with 1/2, it's 1/4. This distance here, there's no way it's going to get close to 1/2. This is almost 1, right? So therefore, this distance is greater than 1/2 if it's squared is greater than 1/4. If this appears in the denominator, what happens? This becomes a maximum. It's a minimum right now, right? As we vary z, this is a minimum, but in the denominator there, it's going to be a maximum. So we can replace it with 1/4 there. The denominator, smallest value, and we'll flip the inequality. Does that make sense? So what about z here? That's absolutely bounded by whatever this number in here. So it's a b minus a, still inequality, b minus a times 0 to 2 pi. On that integral around that circle, the circle never changes. Only b is going to that. So you can say that f is bounded by m on that circle, never changes. And the z here is also never changes there. So that's another absolute value m, and b plus a, there's no z in there. These are all constant number, and that's 1/4, and that's 1 in dt. There's no t anymore here, right? These are all constants. So we accomplished that this one is exactly 2 pi times that stuff that you're looking at right there. All right? So as b approaches a, this thing never changes, except that this one is getting smaller and smaller, and 2a is kind of fixed. So you can see that all of them approaches 0. Is that right? Yeah, b approaches a, and this one is not going anywhere. This is the only part that b and a is involved. They're behaving really nicely. It's approaching 2 times absolute value of a, as b is almost close to that. Right? So that approaches 0. That makes this guy approaching 0. That was primes there, I forgot. So when this is a continuity, what this does is that once the function is continuous, what can you do? Can you differentiate it? Not necessarily. We don't know. There's no way a differentiable function is continuous but not differentiable, right? But what operation is guaranteed when the function is continuous? What's that? Antiderivative. So if you do the antiderivative, and all the other integral theorem applies and tells you it has to be forever analytic, right? And that's the theoretical. So all the integral you use, if you didn't think about it, you can only use it, think about integral before you enter any polynomial. It must be continuous. If you didn't think about that, this whole thing looks like unnecessary thing, but it's a time. When you put antiderivative and integral symbol, before you use any formula, it requires this exists. That existence is coming from the integrand function is continuous. Okay? So we'll continue on Friday here.